Imagine that our entire understanding of the universe, time and space depended on a single energy source that we have barely begun to decipher. What would you do if you discovered that the light bathing our planet now is, in fact, a record of the past that holds the secrets of the most distant galaxies? For centuries, we have looked to the night sky trying to understand the matter and gravity that shape the cosmos, but the answer has always been right before our eyes, hidden in the glow of stars and the behavior of particles traversing the vacuum. Today, this quest has led us to a point of no return in the history and exploration of the solar system, where the evolution of human observation and reach challenges everything we thought we knew about our origins. Many wonder how we know what the sun is made of if we've never gotten close enough to touch it without being consumed. The truth is, our journey of discovery began simply by observing the light from this central engine, learning to read the messages encoded in its photons even before we launched the first probe into the vacuum. This starting point is what allows us today to map interstellar boundaries and question whether there is a real limit to what we can see. When we look at the solar system, we see not only planets and moons, but a living record of a stellar dynamic that dictates the rules of life and destruction on a scale that our minds can barely process. The curiosity that drove us to observe the first solar fusion cycles is the same curiosity that, decades later, gave us the audacity to send machines beyond the heliosphere. We are at a unique moment where technology allows us to combine the study of what is close by, such as the composition of exoplanet atmospheres, with the ability to see through cosmic dust to witness the birth of the first galactic structures. What you will see next is not just a chronology of space missions, but the revelation of how each step we have taken in observing the sun and its outer boundaries has been a cumulative step towards understanding our own existence. What few realize about the beginning of this journey is that science sought not only data, but also the overcoming of an invisible barrier that kept us prisoners of our own atmosphere. If you think space exploration is all about rockets and orbits, prepare to understand how the very nature of light became our greatest telescope. We are about to delve into the mysteries that connect the fiery heart of our system with the absolute silence of interstellar space, revealing why our perspective on the place we call home is about to change forever. What makes our position in the cosmos so unique is the way light acts as a bridge between the observer and the observed object, allowing us to dissect the anatomy of celestial bodies trillions of kilometers away. At the center of it all, the sun operates as a laboratory of extreme physics, where pressure and heat transform simple elements into a complex dance of energy that sustains every form of life on Earth. But this star is not just a lamp in the sky, it is a dynamic entity whose cycles of activity can be felt even at the far reaches of the solar system, influencing space weather and protecting us from galactic radiation through the heliosphere. In this precise millimeter of scientific progress, we have learned that each photon escaping the sun's surface carries a unique chemical signature. By decomposing this light, we can identify the hydrogen, helium, and heavy metals that make up not only the sun, but the basis of everything we know. It's a barrage of facts that hits us daily. The sun converts 600 million tons of hydrogen into helium every second. Its light takes just over 8 minutes to reach us, but the energy generated in its core can take hundreds of thousands of years to fight against the density of matter and finally escape into space. If this energy source were to fluctuate by even a tiny fraction, the delicate balance that allows for the existence of liquid water and oxygen would be instantly disrupted. Mathematics proves that our survival depends on an almost miraculous harmony between solar gravity and Earth's orbit. However, what you are about to see seems impossible if we consider the rudimentary tools with which we began. We went from telescopes made of glass and wood to space observatories operating at temperatures close to absolute zero to capture the infrared light of galaxies that no longer exist. This technological acceleration is not by chance. It is a response to our hunger for answers that simple visual observation could no longer satisfy. We realized that, to understand the macro, we needed to master the micro, the subatomic particles that govern nuclear reactions in the stellar depths. One detail that science has ignored for decades is how cosmic dust acts as a curtain, hiding the nursery of new stars and the secrets of planetary formation. For a long time, we believed that what we saw in the visible spectrum was the totality of reality, but we were only looking at a tiny fraction of the big picture. When we started sending probes to gas giants and beyond, we discovered that the solar system is far more chaotic and diverse than textbook illustrations suggested. There are oceans hidden beneath icy crusts on distant moons, volcanoes spewing sulfur into the vacuum, and storms lasting for centuries, larger than our own planet. Remember this detail well. The same radiation that the sun emits to give us life is the greatest threat to our exploration instruments. This duality between creator and destroyer is what defines the thesis of our journey. If we cannot fully understand the mechanics of this star and how it interacts with the interstellar medium, our ambitions to become a multiplanetary species will be thwarted by a barrier of plasma and magnetism that we have barely begun to map. The solar engine enigma is what keeps us awake, for it holds the key not only to our past, but to the ultimate destiny of everything we orbit. This would perfectly explain everything if it weren't for an inconsistency detected at the outer boundaries, something that defies the laws of thermodynamics that we observe here at the center. It seems that the further we move away from the heat source, the more the rules of the game begin to change inexplicably. Are we neglecting a fundamental factor that only reveals itself in the silence of the deep vacuum? This inconsistency leads us to question the very nature of our cosmic neighborhood. What we discovered by analyzing data from the most recent missions is that the solar system boundary is not a static line, but a pulsating and turbulent frontier. When the first probes crossed the heliopause, they did not find the expected void, but a sudden increase in cosmic ray density and a drastic change in the magnetic field. It's as if we were leaving a protective bubble and entering a vast and unknown ocean, where the sun's influence finally loses the battle to the interstellar medium. This transition is what we call the last gasp of local stellar dynamics, and understanding it is vital for any claim of human reach beyond our neighboring stars. The resolution of this paradox lies in understanding that the sun and the space around it form an integrated and indivisible system. We cannot study the planets in isolation, just as we cannot ignore the impact that the solar wind has on the erosion of planetary atmospheres over billions of years. The evolution of our observation has allowed us to see that what we previously considered empty spaces between worlds is, in fact, filled with plasma, force fields, and energy flows that connect the solar core to the most distant galaxies. We are learning that the matter that composes us was forged in the heart of dead stars long before the sun existed, creating a cycle of renewal that extends throughout time and space. Now that we have established this fundamental basis regarding the engine of our system and the boundaries that surround us, it becomes evident that the next step is the only logical path. We need to delve deeper into the inner workings of this cosmic furnace to understand how it dictates the rules of everything that orbits around it. The foundation is laid. We know light, we understand the importance of gravity, and we have identified the barrier that separates us from infinity. The seatbelt has been fastened, and we are ready for the real acceleration toward the technical knowledge that separates mere observers from true explorers of the cosmos. What we have seen so far is only the preface to a much more complex and fascinating story. We believe that what has been explored so far is the necessary foundation for understanding the anomalies we will find in gas giants and icy areas where the sun is just a bright point in the sky. But there is a question that still lingers, and that no data collected so far has been able to answer satisfactorily. If the sun is the engine of everything, what would happen if its fuel were altered by an external force that we have not yet detected? This is the question mark that will lead us to the next stage of this scientific investigation. To comprehend the immensity of what surrounds us, we must first look at the engine that sustains every gram of matter in our system. The sun is not merely a sphere of light at the center of the map, but a nuclear furnace of unimaginable proportions, where physics reaches states that defy everyday logic. Imagine a cloud of gas and dust so vast that it covered trillions of kilometers, collapsing under its own weight until the pressure at its core was sufficient to ignite the first glimmer of fusion. This event marked the birth of our star, and with it, the imposition of a gravitational order that keeps 8 planets and millions of smaller bodies in an eternal and precise dance. The structure of this giant is divided into layers that function like a perfectly tuned gear. At its heart, the core operates at temperatures exceeding 15 million degrees, transforming hydrogen into helium in a process that releases the energy responsible for everything we know. This energy does not travel quickly. It struggles to traverse the radiative zone and the convection zone, taking thousands of years to finally reach the photosphere, the visible surface that emits the heat we feel on our skin. Understanding this stellar dynamic is the obligatory starting point for any exploration, as the sun dictates not only the Earth's climate, but also the conditions for survival at any point in the heliosphere. Looking at the most recent images captured by probes orbiting the star, we realize that its surface is a sea of constantly boiling plasma. Sunspots and coronal mass ejections are reminders that we live near an unstable power source, whose activity cycles last about 11 years and can directly interfere with our technology down here. This star is the ultimate laboratory, where gravity tries to crush matter while thermonuclear pressure pushes it outward, creating a delicate balance that defines the habitable zone where our planet is located. Without this constant tension, the solar system would be just a cluster of cold rocks and gases wandering in a vacuum. The history of exploring this central engine has evolved from ancient myths to precise spectroscopic measurements. Today we know that the Sun contains more than 99% of all the mass in the solar system, meaning that all the planets, including the giant Jupiter, are mere crumbs compared to its magnitude. This gravitational sovereignty is the anchor that prevents worlds from being lost in the darkness of interstellar space. It is this fundamental thesis, the Sun as origin, sustenance, and regulator, that serves as the basis for understanding why the boundaries of the solar system are so difficult to define, and why human exploration will always have the star as its main guide. Delving into the bowels of this furnace, we find a phenomenon that seems straight out of science fiction: nuclear fusion. Unlike the fission we know on Earth, fusion is the process of joining atoms, releasing such a vast amount of energy that a tiny fraction is enough to illuminate entire galaxies. In the solar core, every second, a mass equivalent to hundreds of millions of tons is directly converted into pure radiation. This is the fuel that powers life, but it is also the origin of a constant wind of charged particles that blows away from the star at speeds of millions of kilometers per hour. This solar wind is not just a space breeze, it is a geophysical force that shapes the magnetospheres of planets and clears the path of cosmic debris. The mathematics of solar stability is what allows life to flourish on a small blue dot. If the force of gravity were slightly stronger, the Sun would consume its fuel in a fraction of the time, making biological evolution impossible. If it were weaker, the star would never have ignited. We are living in what astronomers call the main sequence, a period of stellar maturity that has already lasted 4 billion years and is expected to continue for another 5 billion. During this time, the star acts as a shield. The heliosphere, a giant bubble created by the solar wind, acts as a barrier against the high-energy galactic cosmic rays that would otherwise bombard Earth with lethal radiation. A fascinating detail that often goes unnoticed is the chemical composition we inherited from this initial formation. Through the study of primitive meteorites, we have discovered signatures of iron isotopes that could only have been created in the heart of supernovas. This suggests that our Sun was not born in isolation, but in a dense stellar nursery, possibly triggered by the explosion of a much larger neighboring star. This connection to the universe's violent past shows that the solar system is the result of cosmic recycling. Every carbon atom in your body or the oxygen you breathe has undergone fusion processes, similar to those occurring now in the center of the Sun. The complexity increases when we analyze the solar magnetic field. It is not a straight line, but a tangled web of plasma that twists as the Sun rotates. When these magnetic lines break and reconnect, they release solar flares that can reach Earth in a matter of minutes. These space storms are proof that the solar system's engine is far from silent. They are responsible for the polar auroras, but also represent the greatest challenge for astronauts traveling beyond Earth's orbit. The protection of our atmosphere is what allows us to ignore most of the time the extreme violence that occurs 150 million kilometers away. Remember this fact: the density of the Sun's core is about 150 times that of water, and yet it remains in a gaseous plasma state due to extreme heat. It's a constant struggle between the light that wants to escape and the gravity that wants to pull everything inward. This radiation pressure is what keeps the Sun's volume stable. If this pressure decreased, the star would collapse in on itself, transforming into a dense, cold white dwarf. For now, the balance is absolute, guaranteeing the continuity of time as we perceive it. But this balance comes at a price, and the star itself is slowly becoming brighter and hotter as it ages, changing the fate of the worlds that surround it. This would explain why the search for other star systems always begins with the identification of stars similar to our own. We are looking for that same engine, that same stability that allows for the existence of liquid water. However, when we look at the edges of our own territory, we realize that the Sun's influence is beginning to weaken in ways that classical theory did not fully predict. Is the strength of our central engine being challenged by the interstellar vacuum in a way that alters the very physics of space travel? The delivery of this technical knowledge reveals that the Sun is not just a source of light, but the architect of all the space we inhabit. The study of fusion cycles and plasma dynamics allows us to predict how solar energy interacts with different celestial bodies, from the vacuum of Mercury to the icy clouds of Neptune. We now understand that the stability of the solar system is an emergent property of stellar mechanics. The Sun defines the rules of gravity that govern orbits, the radiation that dictates temperature, and the magnetism that protects or destroys atmospheres. This understanding transforms our view of the sky. We are not just on a planet orbiting a star, but within the extended atmosphere of a vast and powerful stellar organism. Understanding how this energy propagates is fundamental to understanding the evolution of space observation. We have come to see solar storms not as isolated events, but as part of a stellar metabolism that affects the entire system. The integration of data from solar observatories with interplanetary probes has confirmed that the heliosphere is our true safety boundary. Without this engine functioning at its current capacity, the solar system would lose its identity and become just another undifferentiated dust cloud in the interstellar medium. The thesis is confirmed. The Sun is the absolute starting point for any understanding of the cosmos and our origin. With this pillar established, we conclude that mastering solar physics is what gave us the courage and technology to cast our eyes and our machines far away. We assess that the star's inner workings are what generate the pressure necessary to keep the heliosphere bubble intact. However, as we reach the edge of this bubble, the rules that work so well here near the engine begin to fail. What our most distant probes have found when trying to leave this solar protection challenges the vision of an ordered and predictable system that we have constructed so far. The picture that emerges is one of a system that is simultaneously robust and vulnerable. The Sun is our anchor, but it is also the boundary that delimits our direct knowledge. As we conclude this analysis of stellar dynamics, it becomes clear that to understand what lies beyond, we first need to understand how our spacecraft survive the extreme environment that our own star creates. There is a growing tension between the force of the solar wind and the silent pressure of interstellar space that awaits in the darkness. What happens when the engine reaches its limit of influence? And what did pioneering spacecraft detect at that point of transition? This is the mystery that will lead us into the territory of the outer frontiers. If the Sun is the sovereign engine and anchor of all that we know, the Voyager missions represent our first real attempt to test the limits of that authority. Launched in 1977, during a rare planetary alignment that occurs only once every 175 years, these two spacecraft were sent on a one-way journey into the unknown. The plan was audacious: to use the gravity of the gas giants as slingshots to catapult human-made instruments to the outer edges of the solar system. What these machines encountered over decades of travel transformed our vision of an ordered system into a scenario of extreme complexity and isolation. The trajectory of these probes allowed us, for the first time, to see up-close worlds that were previously just blurs in terrestrial telescopes. Voyager 1 and 2 revealed Jupiter's great red spot in mesmerizing detail, Saturn's intricate ring systems, and the icy atmospheres of Uranus and Neptune. But the real challenge began when they left the planets behind. From then on, the mission became a silent search for the point where the solar wind finally loses its strength. This territory, known as the outer frontiers, is where the physical influence of the Sun begins to give way to the hostile environment of interstellar space, challenging our capacity for communication and technological survival. Human reach has been brought to its peak with these machines, which today are more than 20 billion kilometers away. They operate in an environment where sunlight is so weak that the star is nothing more than a bright, distant point, incapable of providing enough heat or energy for solar panels. To continue functioning, the Voyagers rely on radioisotope thermoelectric generators, transforming the heat from plutonium decay into electricity. It is this autonomy that still allows us today to receive data on plasma density and cosmic ray intensity at the periphery of our system, revealing a panorama that contradicts many of the initial theoretical predictions. The evolution of observation reached a critical point when these probes crossed the heliopause. This milestone was not just a technical achievement, but a paradigm shift. We realized that the boundaries of the solar system are neither empty nor silent. They are shock zones, where charged particles from other parts of the galaxy collide with the protective bubble created by the Sun. This antithesis to the controlled and familiar environment we have here, near the central engine, shows that space exploration is, ultimately, a fight against oblivion and degradation in a vacuum that was not made for us. What the Voyagers detected as they approached the edge of the solar system was an unexpected and dramatic increase in the pressure of the interstellar medium. For years, it was believed that the transition would be smooth, a gradual decline of solar influence until total vacuum. However, the instruments recorded what scientists call a termination shock, a region where the solar wind abruptly decelerates from supersonic to subsonic speeds upon encountering external resistance. It's a machine gun of invisible facts. The plasma temperature in this zone rises suddenly, and the magnetic field becomes chaotic, creating a barrier of turbulence that protects the inner system, but also makes it difficult to read what lies beyond. The mathematics of communicating with these spacecraft is a testament to our persistence. A radio signal sent from Earth takes more than 22 hours to reach Voyager 1. The return of that signal, carrying precious data about interstellar space, requires near-impossible reception precision, utilizing gigantic antennas of the Deep Space Network. In late 2023, a memory error in Voyager 1's flight data system threatened to silence the spacecraft forever, sending only a meaningless stream of zeros and ones. The successful recovery of this communication, through reprogramming done billions of kilometers away, proved that human ingenuity can overcome the limitations of aging hardware under extreme conditions. One detail that alters the perception of the solar boundary is the discovery that the heliosphere is not a perfect sphere, but has an elongated, comet-like shape due to the Sun's movement through the galaxy. This means that the distance to interstellar space varies depending on the direction of travel. The Voyagers crossed the boundary at different points, revealing that the solar bubble is porous. High-energy cosmic rays can penetrate through magnetic slits, providing samples of matter that do not belong to our original system. It's as if we were studying the ocean through small cracks in a submarine hatch under immense pressure. The complexity of the outer boundaries also includes the mysterious Oort cloud, a colossal reservoir of icy objects stretching nearly a light-year across. Although the Voyagers have crossed the heliopause, it will still take them hundreds of years to reach the beginning of this cloud and tens of thousands of years to traverse it completely. This redefines what we call a boundary. If we consider gravitational influence, the solar system is vastly larger than the zone of influence of the solar wind. This distinction is fundamental. We are physically in interstellar space, but still trapped in the gravitational embrace of the Sun. Remember this fact. Voyager 1 travels at about 60,000 kilometers per hour relative to the Sun, and even so, it will take it about 40,000 years to pass within just 1.6 light-years of a neighboring star in the constellation Ursa Minor. The isolation is absolute. The interstellar space they are now traversing is filled with a plasma much colder and denser than the solar wind, composed of remnants of supernova explosions that occurred millions of years ago. The probes are literally navigating through the history of other stars, serving as our eyes in a territory we will never be able to visit personally in our lifetime. This would explain why measurements of external radiation are so crucial for planning future manned missions to Mars and beyond. If the heliosphere were not so efficient at filtering these galactic particles, life on Earth would have faced much greater evolutionary challenges. However, when we analyze what is out there, a contradiction arises. Why does the interstellar environment seem so rich in information about the origin of the universe, while our internal system seems so clean of this evidence? Could the Sun be an agent that erases traces of the distant past to create its own order? The delivery of this technological reality shows that our understanding of outer boundaries is the result of heroic resistance against time and cold. The Voyagers revealed that the solar system does not end where the planets end, but where the Sun's energy reaches its limit. The mapping of the heliopause and the detection of direct interstellar plasma validated that we live protected by a dynamic bubble whose integrity depends on the central engine we discussed earlier. This phase of exploration proved that space is not a static void, but a battlefield of magnetic and thermal forces that define the reach of any technological civilization. The resolution of this conflict between the solar wind and the interstellar medium allowed us to refine our models of how stars interact with their galaxies. We learned that the solar system is an open entity, constantly exchanging matter and energy with the outside world, despite the protection of the heliosphere. The integration of Voyager radio data with observations from space telescopes created a three-dimensional view of our boundaries, showing that direct exploration, however limited, is irreplaceable. The antithesis is complete. The ordered system of the center gives way to the controlled chaos of the periphery, where humanity left its first permanent fingerprints. With this pillar consolidated, it becomes clear that our capacity for physical reach has reached a temporary limit. We assess that the Voyagers are our scouts in the darkness, but that their 50-year-old technology is no longer sufficient to answer the new questions that their own journey has generated. The next logical step is not just to travel further, but to see better. We need a new tool that doesn't depend on physically traversing space, but that can decipher the messages that light brings from the depths of time, overcoming the heat of the sun to see the cold of the beginning of everything. The panorama left by the Voyagers is an invitation to humility and innovation. They are time capsules carrying our music and our location, destined to wander through the vacuum long after their transmitters have fallen silent. As we close this chapter on outer frontiers, we prepare for a new form of observation that unites the study of what is near with the vision of what is infinitely far. There is an urgent need to reconcile the life-producing heat of the sun with the need for absolute cold to observe the deepest secrets of the cosmos. How can we see the invisible without being blinded by our own star? The evolution of observation reached a critical impasse. While the Voyagers gave us a physical glimpse of the boundaries, our eyes needed a sensitivity that the heat of the solar system itself made impossible. The answer to this dilemma came with the James Webb telescope, an engineering marvel that cost $10 billion and took decades to complete. It was designed not only to take sharper pictures than Hubble, but to operate at a frequency that allows us to penetrate the curtains of cosmic dust. To achieve this, it had to be folded like origami, to fit inside a rocket and sent to a point of gravitational equilibrium 1.5 million kilometers from Earth. The great challenge of this technological synthesis is temperature. James Webb studies infrared light, which is essentially heat radiation, coming from objects so distant that their light has been stretched by the expansion of the universe over billions of years. If the telescope were near Earth or pointed at the sun, its own internal heat and solar radiation would blind its ultra-sensitive sensors. Therefore, it carries a thermal shield the size of a tennis court, composed of 5 layers of a material called kapton, which keeps its mirrors at temperatures close to absolute zero, while the other side of the shield boils under direct sunlight. This duality between the extreme heat of the solar engine and the cold necessary for deep observation is what defines the mission's success. James Webb is not just a telescope, it's a time machine. By capturing the oldest photons in the universe, it allows us to see the formation of the first galaxies and the birth of the first stars that emerged shortly after the Big Bang. It unites the study of what is close at hand, such as the chemical analysis of exoplanet atmospheres in search of signs of life, with the vision of the most remote origins of matter and energy. It is the meeting point between our solid foundation in the solar system and our curiosity about the infinite. Human reach, which once depended on sending physical probes to traverse the vacuum, now expands through the capture of invisible data. James Webb proved that to understand the whole, we need to hide from the light of our own star. This strategy of indirect and shielded observation revealed images of stellar nurseries and galaxy clusters with a precision that defies our previous perception of space. We are now in an era where the synthesis between infrared technology and orbital stability allows us to map the universe with a depth that previous generations could only dream of. The James Webb Telescope's precision lies in its ability to detect thermal signals so faint they would be equivalent to the heat of a bee on the surface of the moon, as seen from Earth. This extreme sensitivity is what allows the telescope to perform transmission spectroscopy on planets orbiting other stars. When an exoplanet passes in front of its star, the light passes through its atmosphere, and Webb can identify signatures of water, methane, and carbon dioxide. This is a data machine. In just a few months of operation, the telescope has already found evidence of sand clouds on distant planets and carbon-rich atmospheres that may be fundamental to the chemistry of life. The mathematics of its orbit at the Lagrange point L2 is what ensures it always remains aligned with Earth, protecting itself from the sun. Unlike Hubble, which orbited Earth and was affected by its light and heat, Webb is in a location where the gravity of Earth and the sun combine to keep it in a stable position with minimal fuel consumption. However, the risk is immense. At this distance, there is no possibility of repair missions by astronauts. Each of the 300 potential failure points during its deployment in space had to be executed with absolute perfection. from the opening of its gold-plated hexagonal mirrors to the precise tensioning of the layers of its heat shield. One detail that alters our understanding of time is the redshift effect. As the universe expands, the light from the oldest galaxies is stretched, moving from the visible spectrum to the infrared. The James Webb Space Telescope was specifically built to see this stretched light. It is observing objects that emitted their light more than 13 billion years ago, just a few 100 million years after the beginning of everything. This means that when we look at Webb's deep images, we are not seeing what the universe is like now, but rather its infancy, revealing how gravity began to clump matter together to form the first galactic structures. The complexity of cosmic dust, once an insurmountable barrier, has become transparent to Webb's eyes. In regions like the pillars of creation, where Hubble saw only dark, opaque clouds, Webb can see through the gas, revealing thousands of young stars forming within. This penetrating ability is vital for understanding how our own sun and solar system formed from similar nebulae. We are observing the cosmic recycling process in real time, seeing how the death of massive stars fertilizes space with the heavy elements necessary to create rocky worlds and living beings. Remember this fact: the James Webb Space Telescope's primary mirror is 6.5 meters in diameter, offering a light-gathering area 6 times larger than Hubble's. This gigantic scale is what allows it to capture the faintest signals from the deep universe. However, this same power requires an active cryogenic cooling system for one of its instruments, MIRI, which needs to operate at just 7 degrees above absolute zero. Without this extreme cold, the telescope itself would shine more brightly than the targets it attempts to observe. It's a triumph of thermodynamics applied to the pursuit of absolute knowledge. This would explain why James Webb is considered the scientific successor to all previous missions. It synthesizes the local exploration of the Voyagers with the panoramic view of large ground-based observatories. However, as we reveal these images of the first galaxies, a new question arises that challenges our cosmological models. Some of these galaxies appear to be much more massive and evolved than previously theorized for such an early stage of the universe. Are we misinterpreting the chronology of matter, or is there a hidden factor in the evolution of galaxies that infrared light is only beginning to show us? The delivery of this scientific synthesis demonstrates that our ability to understand space and time depends on our skill in reconciling extremes. The James Webb Space Telescope proved that we can use technology to overcome the limitations of our biology and our location in the solar system. By hiding from the sun's heat to capture the cold of the early universe, the telescope validated the thesis that light is the ultimate tool for exploration. The integration of precision engineering and theoretical astrophysics allowed us to see the invisible, transforming what were merely mathematical hypotheses into clear visual evidence of our cosmic origin. The resolution of this observation cycle shows that James Webb doesn't replace physical missions like the Voyagers, but complements them vitally. While probes tell us what the space around us is made of, the telescope tells us where we came from and where the universe is headed. The synthesis is complete. We now understand that the evolution of observation is a process of constant refinement, where each new tool allows us to look a little further through the darkness. Webb's success is proof that humanity is ready to face the most fundamental questions about life and the structure of reality. With this foundation established, we realize that each discovery made by the James Webb Space Telescope opens a dozen new doors that we don't yet know how to cross. We validate that our vision of the cosmos is now deeper and clearer than ever, but we also recognize that the more we see, the more we realize how much still remains hidden. The groundwork is laid for the conclusion of our journey, where we will unite the lessons of the solar engine, the reach of outer frontiers, and the vision of deep time to project the future of our species among the stars. The emerging panorama is that of a civilization that has begun to decipher the language of the universe. The James Webb Space Telescope is our most powerful translator, revealing the chemical signature of distant worlds and the glow of primordial galaxies. As we conclude this analysis of the synthesis of modern observation, we prepare for a final reflection on the meaning of all this cumulative effort. One last gap in understanding awaits us. If the solar system is only a small stage in this cosmic arena, what is the real value of our relentless pursuit of frontiers that seem to recede with every step we take? Looking back, we realize that our journey through the cosmos is a succession of steps built upon curiosity and the overcoming of physical limitations. We began this exploration in the beating heart of the solar system, understanding the Sun not just as a star, but as the fundamental engine that dictates the rules of gravity and energy. Without understanding stellar dynamics and fusion cycles, we would never have had the theoretical basis to launch our first vacuum machines. Every particle of light we analyzed and every solar storm we monitored were vital lessons that prepared us for what was to come. The challenge of breaking through the protective bubble of the heliosphere. The contradiction we faced along this path was clear. On the one hand, the Voyager missions pushed human reach to the limit of what was possible, physically touching the interstellar medium and revealing the porous nature of our boundaries. On the other hand, these same machines, while resilient, showed the limitations of our physical technology in the face of the abyssal distances of the universe. This tension between the desire to travel and the impossibility of doing so in a timely manner created the need for a new approach. It was here that the conciliatory factor emerged, the deep vision of the James Webb Space Telescope, which synthesized the need to hide from the heat of our own star in order to see the origin of all that exists. This panoramic view now allows us to see the solar system not as an isolated system, but as part of a continuous cosmic fabric. The history of our observation has evolved from looking at planets as distant gods to understanding them as complex geological worlds, and finally to seeing them as byproducts of a galactic evolution that began billions of years ago. What unites the Sun, the Voyagers, and Webb is the same common thread, the quest to understand the matter and energy that compose us. We are at a point where accumulated technical knowledge allows us to map the past to try to predict the future of our presence in space. The conclusion that emerges from this analysis is that space exploration is an exercise in humility and persistence. Each discovery, from the composition of the solar core to the first galaxies sighted by Webb, is a reminder that we are a species of explorers by nature. The solar system was our nursery, but the tools we developed to understand it have become the keys to unlocking the doors to the deep universe. The foundation is solidified, and the paradoxes between the heat of creation and the cold of observation have been reconciled by our engineering, leaving us before the final frontier. What will we do with this knowledge? The ultimate connection between the solar engine, the outer frontiers, and infrared vision reveals a profound truth about our existence. The Sun provided the elements through fusion. The Voyagers mapped the space where these elements were organized, and James Webb showed us that this process is universal and repeats itself in every corner of the galaxy. This integration shows that the study of the solar system is, in fact, the study of ourselves. There is no real separation between the chemistry of a distant star and the iron that runs in our veins. Space exploration is how the universe seeks to understand its own complexity through our eyes and instruments. At this final stage, the shift in tone is inevitable. As we observe the vastness revealed by Webb Space Telescope, the feeling of isolation conveyed by the Voyagers transforms into something grand. We realize that, although we are small on a pale blue dot, our minds are capable of reconstructing 13 billion years of history simply through the analysis of light. The contradictions between the protection of the heliosphere and the aggressiveness of the interstellar medium cease to be obstacles and become characteristics of a dynamic system of which we are a part. Our science is not merely an accumulation of data, but a bridge we have built to cross the abyss of the unknown and give meaning to the vacuum. Exploring the ultimate contradictions reveals that the more we know, the deeper the mystery becomes. We discover that the matter we see is only a fraction of what exists, and that the forces shaping galaxies may be linked to phenomena we haven't even been able to name yet. This realization is what drives us into the future. The success of past and present missions is not an endpoint, but an incentive for new questions. What remains in the shadows is not fear, but the promise of new revelations that will once again challenge everything we thought we had consolidated here in the comfort of our star. The silence preceding the final revelation is the acknowledgement that we have reached the limit of what our current observational technology can tell us about the why. We have the how and the when, but the last gap in understanding remains open. We are on the threshold of a new era where artificial intelligence and quantum physics may be the new telescopes to peer into what James Webb cannot yet see. The universe is a book we are only beginning to read, and each cycle of discovery is a page turned that reveals an even more complex and beautiful narrative. The final word on the exploration of the solar system and the evolution of observation is that progress is cumulative and irreversible. The resolution of all the paradoxes presented lies in our capacity for adaptation. We use the sun's heat to launch ourselves, the cold of space to see, and the distance of the frontiers to measure our own courage. The closure of this loop, begun with light and particles, takes us back to the starting point, but with a completely transformed perspective. The sun is no longer just a light in the sky, but a witness to our growth as a technological civilization capable of deciphering the code of time and space. The content of this narrative connects the internal structure of the sun with the fate of the Voyagers and the images from Webb in a unique narrative of human triumph. We believe that each step of this journey was necessary for the next to exist. Without the study of stellar dynamics, there would be no probes. Without mapping the boundaries, there would be no need for deep infrared telescopes. This is the logic of science, a generational effort that ignores political boundaries to focus on the final frontier of knowledge. The solar system is our initial laboratory, and the lessons we learn here are the laws we apply to the rest of the universe. Thus we conclude the development of this itinerary, having journeyed from the depths of the sun to the limit of observable light. The final deliverable is the understanding that exploration is endless, for each limit reached becomes a new starting point. The future of human observation is already being shaped, with telescopes that have sought signs of biology on other worlds and spacecraft that may one day surpass the speed of our pioneering Voyagers. What began as a curious observation of the stars has become our greatest adventure, and the roadmap for what comes next is being written now by each of us who dares to look up. The final gap in understanding, the silence that precedes the revelation, is the question that remains for the viewer. If we were able to come so far with such simple tools, what will we be able to discover when we finally master the laws of matter and energy that the sun taught us to read? The solar system is only the beginning of a story that humanity is still learning to tell.